This is Lab 4, the magnetic dipolar field for Physics 2212. The purpose of this lab is to measure the magnetic field versus distance due to a bar magnet and compare the measurements to the expected outcomes from application of the Biot-Savart law. In this lab, I measured the parallel and perpendicular magnetic field of a small bar magnet using my phone's magnetometer. First, I aligned my y-axis to the Earth's magnetic north-south axis to minimize noise. I then found the magnetometer's location in my phone. Then, I measured the magnetic field at different distances along the x and y axes and plotted them in a spreadsheet. These are the fundamental physical principles. The Biot-Savart law for a magnetic dipole is mu naught over 4 pi times 1 over r cubed times 3 times mu dot r hat times r hat minus mu, where mu is the dipole moment and r hat is the direction of the dipole. And then so that creates two different magnetic fields. On axis, B equals mu naught m over 2 pi r cubed. Off axis, B equals mu naught m over 4 pi r cubed, where m is the magnetic dipole. So for this experiment, the system was the small bar magnet, and the surroundings were the phone, table, and measuring tapes. Initial conditions were the net magnetic field in Atlanta is 49 microtesla, so we had to account for that by zeroing all our stuff. I measured the distance at magnetic fields of 20, 70, 120, 170, and 220 microtesla and plotted LNB versus LNR to find the distance dependence of the magnetic field. In this lab, we modeled the bar magnet with the equation B equals K times R to the N. Therefore, LNB equals LNK plus N LNR. Since the slope of our equation is approximately -3, actually it's like -2.95, we find that N equals -3, so it has a 1 over R cubed dependence. From this, we can solve the equation and find that K is approximately 6 times 10 to the -7. This is my code for the off-axis magnetic field. In this code, I defined a function for the dipole, and then I created a bunch of locations to measure that at, both on the axis and perpendicular to the axis. And then I just did the same thing a bunch of times, copying the starter code, where it gave R perp, it gave B perp, it created an arrow, and then it printed the actual value of the magnetic field. And then the last part was to find the magnetic field at a 45-degree angle. And so I set that up with D perp instead of R perps. And I put my actual value from the experiment in there, modeled it in the code, and then modeled it here. So this is what my code gave as a result. It gave a bunch of B axes and B perps. And so it ended up being the B at 45 degrees was 2.6 times 10 to the -6, 8 times 10 to the -6, 0. And my measured B of D was 8 times 10 to the -6, 0, -7 times 10 to the -6. I suspect my axes are slightly different in code versus in the experiment. And I also suspect that mismeasurement is probably the cause of this, because my phone's magnetometer is not particularly accurate, and there are just a lot of ways to, a lot of sources of error. If I hadn't oriented my experiment to compensate for magnetic north, my results would have an extra component related to the angle with respect to north and the magnitude of the Earth's magnetic field. It would have increased the difficulty of determining the strength of the magnetic field due to the bar magnet, as it would be hard to untangle both fields. If I were to stick two identical magnets together end to end and run the experiment, I would expect the magnetic field to cancel out. For the magnets to stick, the magnetic dipoles would have to face in opposite directions, which cancels them in the far field. In this lab, I analyzed the distance dependence of a magnetic field created by a small bar magnet. I measured the field both parallel and perpendicular to the magnet. Furthermore, I created a model to calculate the off-axis field of the bar magnet and compared it to my experimental results.